Okay, so ideally today we're going to look at transformations of functions, and you should be able to translate functions horizontally and vertically, be able to stretch them or compress them, the entire function, and understand the transformations of A, H, and K, specifically how they relate to quadratics. So you made these sliders in the past last semester, and you originally graphed y equals x squared. So we're going to compare each of these functions to the function y equals x squared. So that's what's outlined here in both red and green. So we're going to look at x squared plus 4. So in other words, we're going to change k to 4. So we've got x squared plus 4. You can see our green function compared to the red function, which is x squared, it just simply was translated up 4. Translate means to slide, so it slid up 4. Okay, and then if we make, in this next one, x squared minus 3, so in other words, k is negative 3, we can see it's the exact same function, it just slid down 4. It translated down 4. Oh, sorry, down 3. Okay. Next we've got, so we'll put k back to 0. And in this next example, x minus 3, the quantity squared, so h is negative 3. And we can see that moves our function right 3. So that's a bit odd. A negative 3 moves our function to the right 3. And when h is positive 4 in this next example, so plus 4, notice it moves the function left 4. So based on that, we should be able to draw some conclusions. So k is going to move our function up or down, and h, the variable inside the brackets, is going to move our function left or right. And we'll summarize those in the next slide after this one. So we're going to look at these transformations. Transformation just refers to change, to transform the graph. So these are all related to the variable a. If y equals 2x squared, so a originally in y equals x squared is 1, so we're going to change a to 2. And you can see our green function just got a little skinnier than our red function, y equals x squared. So y equals 2x squared is skinnier than y equals x squared. Okay, if we look at y equals 5x squared, just like you would expect, if we make a 5, it's going to be even skinnier yet. So 5x squared is even skinnier. We can call this a vertical stretch. If you can imagine the function being stretched vertically, it's being pulled in a vertical direction. So these are both vertical stretches. Okay. When a is 0.1, 0.1, you can see our function is super wide. It's much, much wider than y equals x squared. Okay, and when a is when a is 0.5 in the next example, it's still wider than y equals x squared. Not as wide as 0.1 x squared, but still wider than y equals x squared. Okay, so we can call this a vertical compression. If you can imagine our function being compressed vertically. It's being kind of pushed down upon, made wider. And when a is negative, so in this next example, is -2. So you can see our function is skinnier once again, and it's flipped over the x-axis. So it's a reflection over the x-axis. X-axis. And that's all because a is negative. So the fact that it's reflecting over the x-axis makes is just due to the fact that a is negative, and the fact that it's a -2, not a -1, is going to make it, again, skinnier than y equals x squared. And just like you'd expect, when a is -5, it's going to be even skinnier, and it's still going to be reflected over the x-axis. So same thing, just even skinnier. So when we have a -a, we're going to have a reflection over the x-axis. Okay. So let's just summarize these transformations. We'll put a back to 1. Okay, h, remember, is within the bracket. So if we make h positive, our function moves left, and if h is negative, our function moves right. So it's the opposite of what you would expect. So if h is positive, it's going to the left. Positive h left. And if h is negative, it's shifting to the right. If k is positive, so make h 0 again. If k is positive, just like you would expect, it's going to move our function up. If k is negative, our function is going to be moved down. So vertical shift positive, vertical shift negative. If a is greater than 1, we talked about those examples just recently. If a is greater than 1, it's going to be skinnier. So we're going to call that a vertical stretch. Our function is going to be stretched vertically. It's going to get skinnier. If a is between 0 and 1, like in these two examples, 0.1 and 0.5 are both values between 0 and 1, we're going to have a vertical compression. Our function is going to be wider than y equals x squared. The graph of -f of x, so that refers to when a is negative, we're going to have a reflection over the x-axis. Okay, and if we have f of -x, I didn't really look at this, but if we're plugging -x in for x of the function, so if we replace this x with a -x, it's actually going to switch the value of our h, really, and that's just going to be a reflection over the y-axis. And we will talk more about those two specifically in the future, but for now you should really get out of this that if a is negative, it's going to flip that parabola upside down. We're going to have a downward opening parabola. The graph of f of -x we'll definitely look at more in the future. That's just a brief introduction to it right now. Okay, so if you can pause the video and describe the transformations of the following quadratic functions. I'm going to do the same thing for you, and when you're ready, hit play again, and you can reveal the answer. Okay, this first example, 2 times the quantity x plus 4 squared minus 3. We can see that a is 2, so our function is graphed here, this green one. Our function is stretched vertically, it's skinnier. H is equal to a positive 4, which means the function moved left 4. You can see it moved left when h is positive. And k is -3, so you can see the function, the vertex, moved down 3. So the vertex essentially moved left 4 and down 3. Okay, next example, we've got a is -2, so we can see our function opens downward. It's a reflection over the x-axis, and the 2 part of it, the quantity 2, means we have a vertical stretch. So our function is skinnier than y equals x squared. H equals -3, so our function moved right 3. You can see the vertex moved from 0, 0 here to an x value of 3, and k moved up 4. So k caused our vertex to move up 4, and the entire function shifted up 4. Okay, last example, you can see a is 0.5, so we have a vertical compression. This green function is wider than y equals x squared. H is +4, so our function moved left 4. You can see the vertex moved left 4. And k is -3, so our function moved down 3. So you can see our new vertex is at the point -4, -3. Okay, so we don't always have to work with the function y equals x squared. What if y equals the square root of x and we want to translate the function 2 units right and 3 units down? So we're going to use the same principles. We're still going to talk about h and k. So if you think back to the idea of the quadratic function, if we want to move our function to the right, h is going to have to equal -2. And if we want to move our function down, k is going to have to equal a -3. Okay, so what that looks like with y equals the square root of x, our h will be right here within that square root, and then k is outside of the function. Okay, so we've got our function moving to the right 2, that's what the -2 within the function does, and outside of the square root, outside of the function, k is going to move our function when it's negative down. Okay, if we're given this function, which is an absolute value function, we should be able to graph the following transformations. So I'm just going to get rid of my calculator. Okay. So basically, we know that every single point is going to be moved to the left 1. You can see that h is 1. It's within this function, and we're adding 1. So it's going to actually move every point to the left 1. So let's start with that. So instead of the point 2, 0, we're moving left 1, so we're going to be at 1, 0. Instead of 0, 3, we're moving left 1, so it's going to be -1, 3. And instead of the point 4, 3, we're moving left 1, so it'll be 3, 3. Okay, so they all just moved left 1 because h is +1. Okay, now we want to multiply every single y value by 4. So we've got the point, and that's what a is telling us to do. So we've got the point 1, 0. We're going to multiply y, which is 0, by 4. So 0 times 4, we've still got 0. So that point can stay right where it is. That's the final point. We're going to do the same with this point here. We've got the point 3, 3. We're going to multiply y by 4. So 3 times 4 gives us 12. So really, we're going to keep our x value the same, and we're going to move y up to 12. So we've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, somewhere off the graph here. And notice the same thing is going to happen with our other point. We've got the point -1, 3. When we multiply the y by 4, we're going to get the point -1, 12. So that is going to be also way off the graph. And then it's just a matter of connecting those points. Okay, so you can see our function moved left 1 based on the fact that h was +1. And we had a vertical stretch. It's as if someone grabbed that function and stretched it vertically upwards. Okay. F of -x -2. So this f of negative x is a reflection over the y-axis. And remember, negative f of x, just for your information, is a reflection over the x-axis. So if the negative is outside the function, it reflects over the x-axis, so it would flip it over downwards. But this is a reflection over the y-axis. So all of these points are going to be, it's as if the y-axis is a mirror, and it's going to be reflected to the left. So that point 0, 3, that's the y-intercept, is going to stay exactly where it is because it's already on the y-axis. The point 2, 0, instead of positive 2, 0, if you can imagine, we start here, we're going to reflect it over the y-axis, and we're going to be at negative 2, 0. And same thing with 4, 3. So if we start at 4, 3, that point is going to be reflected over the y-axis, and we'll be at negative 4, 3. So that takes care of the y-axis reflection. And then k is negative 2. So that tells us to move our function down 2. So every single one of those points is going to move down 2. So this point is moving down here. We've got the point negative 2, 0 is moving down 2, and this point here is moving down 2, and that's it. We can then connect the dots. We've got our function transformed based on a reflection over the y-axis and move down 2, and that's okay. Okay, last thing, horizontal stretch. So if we have any kind of number, any constant being multiplied by x within our function, the effect is going to be a horizontal stretch of the graph by a scale factor of 1 over whatever that constant is. So you can imagine, say we have the function y equals the square root of 2x, and we're comparing it to y equals the square root of x. Okay, so in this case, our q that we're referring to is greater than 1. 2 is greater than 1. So it's going to move the points closer to the y-axis. It's going to be a horizontal shrink. Okay, and if we had instead y equals 1/2 times x all underneath our square root, 1/2 is between 0 and 1. So it's going to move the points of our function further away from the y-axis. So we can call that a horizontal stretch. So we're talking about affecting x. So xy, the mapping, is that xy is going to go to x divided by q comma y. Y will just stay the same. It's not going to affect it. It's the x that's going to change. So in the first example we looked at, xy, the point xy is going to go to x divided by 2, 2 is our q, comma y. So every x value is going to be divided by 2, but keep the same y value. So you can imagine those points are going to grow closer to the y-axis. It's going to be a horizontal shrink. Whereas in the second example, xy is going to go to x divided by 1/2. Okay, x divided by 1/2, comma y, which dividing by 1/2 is the same as multiplying by 2. The reciprocal of 1/2 is 2, so it's going to go to 2x, comma y. Every x value is going to be multiplied by 2, so you can tell that those points are going to be stretched horizontally. That function is going to have a horizontal stretch. We'll look at some examples of that. Okay, so we've got our original function. It happens to be a parabola. We're going to look at f of 2x. So remember the mapping. xy is going to go to x over whatever our q is. In this case, q happens to be 2. So x over 2, comma y. So every y value is going to stay exactly the same. It's the x's that are going to be divided by 2. Okay, so we're going to do that to each one of these x's. So we're going to divide -1 by 2, we're going to divide 1 by 2, and 2 by 2, and we're going to map these new points. So we've got the point -1/2, 1. The y value stays the same. We've got the point 1/2, 1. And we've got the point 2 divided by 2 is 1. So 1, comma, 1, 2, 3, 4. And that is our new parabola. Something like this. Okay. So you can tell this is a horizontal shrink. We took the parabola and we shrinked it closer horizontally towards the y-axis. Okay, next example. Notice first of all that our q is 1/3. So x divided by 1/3 is going to be the same as multiplying by 3. So our mapping xy is going to go to 3x, and y is actually going to be subtracted by 1. K is going to move every y value down 1. So y minus 1. Okay, so we're going to multiply each x value by 3. We're going to subtract each y value by 1. So -1 times 3 gives us a -3. 1 minus 1 gives us 0. 1 times 3 gives us 3. 1 minus 1 gives us 0. 2 times 3 gives us 6. 4 minus 1 gives us 3. So we've got -3, 0. We've got 3, 0. The point 0, 0, that's a nice one to have. What is this going to change to? So 0, 0 is going to be multiplied by 3, the x value, so that's still going to be 0. And the y value is going to be moved down 1. And, okay, and then we have the point 6, 3. 1, 2, 3, 4, 5, 6, 3. Okay, so something like this. So you can see our function has been stretched horizontally. It's grown further from the y-axis, and it's moved down 1 because k is -1. Okay, so that's a horizontal stretch compared to a horizontal shrink in that previous example. Yeah, and that's it. Thank you.